welcome back. I hope you can all hear me. Still, good morning from Newcastle, and good afternoon to Czech Republic, to Jiří Kmošek. I would like to introduce him. He's a PhD candidate at the Institute of Science and Technology in Art at Academy of Fine Arts, Vienna, and he's also a researcher at the Nuclear Physics Institute at the Academy of Sciences of the Czech Republic in Hřeš, near Prague. And we have been long-time collaborators, more than 10 years. And in this talk today, he would like to tell you more about some specific archaeometallurgical methods that can provide us information about the production technologies and also practical possibilities of the tool use. And he will be focusing especially on metallography, Vickers microhardness, and portable X-ray fluorescence. And the special focus of the talk will be on the collection of Egyptian and Nubian artifacts in Leipzig in Germany, where we have been kindly allowed by the then curator of the collection, Dietrich Raue, to sample a wide selection of artifacts, and also by the conservator of the collection, Herr von Stulpnagel, to really provide some information about the artifacts in their collection. Jiří, the floor is yours.
Hello, everyone. Thank you, Martin, for the invitation to present on this webinar. And as a part of my lecture, I will introduce you to the analytical methods of metallography, microhardness tests, and mobile X-ray fluorescence spectrometry, and application of these techniques to study of Egyptian tools made of copper alloys, mainly arsenical copper. The analyzed tools come from the Egyptological collections of the Egyptian Museum of the University of Leipzig in Germany and the study collection of Prehistoric Institute of Vienna University, Faculty of Arts, and were published within these two main studies. Metallographic methods, or more precisely methods of microstructural analysis of metallic and related metallurgical materials, are most often used in cases where we want to learn more information about the production techniques of artifacts, their mechanical properties, or specific aspects associated with the distribution of certain metallic or non-metallic phases or corrosion phases. The disadvantage of this method, as it is destructiveness, requiring sampling of at least 5 cubic millimeters from technologically important artifacts locations. Currently used methods of elemental and isotopic analysis are much less destructive, and sampling by the drilling method is also less invasive. Currently, we use the method of microstructural analysis mainly in the analysis of metallurgical material such as slags, pearls, ingots, crucibles, or other metallic byproducts, and also some final artifacts. Methods of microstructural analysis are also relatively well available in Egypt, and we can be therefore very well applied to study archaeological material from ongoing research at archaeological sites. And there are also much more possibilities to sample the objects and to carry out such research. The preparation of samples includes standard procedures such as mounting of samples in epoxy resin, grinding, polishing of the surface of the specimens, and alternatively, metal samples are etched with suitable chemical agents to highlight the inner microstructure of the metallic samples. Subsequently, the samples are observed and documented using optical polarized microscopes and additional microstructural analysis for specific phases using scanning electron microscopes equipped with EDS or VDS analyzers, allowing us a detailed elemental analysis of some specific microstructure features. And if it is necessary and we are not sure with interpretation some specific phases or corrosion products and so on present in the microstructures, we need to use the method of X-ray diffraction phase analysis to perform the phase analysis and to clarify our findings from previous studies. I'm not sure how the listeners are familiar with the microstructure features of FCC metals, but for sure I will try to explain a little bit how it works and what we can see in the microstructures. I would like to show you this illustration. This is very important, how do I understand the inner microstructure of samples which we are working on. Copper and its alloys crystallize in the form of face-centered cubic structure, like also nickel, silver, gold, and high temperature gamma modification of iron and its alloys. And the initial cast material, I'm not sure if you see what I'm marking. No. The initial cast material showing dendritic microstructure with specific segregated and cored structure. An extensive annealing, it means heating of material in temperature higher than 3 degrees of Celsius, completely changed the dendritic microstructure into the form of such more regular hexagonal grains. And this annealing removed the segregated and cored structure completely. If we apply some cold working, it means cold hammering, forging, or other mechanical ways of material forming, we will get such deformed hexagonal grains with specific features like these lines, which we called like strain lines or slip lines. And these are indicating the mechanical forming of material. And in another step, if we apply some recrystallization annealing on such a mechanically worked sample, we will get again completely recrystallized structure, but we can see some new feature inside, and these are such twin lines inside of the grains, which are indicating previous cold or hot working. And these are still visible after some cycles of annealing. And if we continue with cold working, the microstructure looks very similar like before, but in final step of annealing, we can see after repeated cycles of cold working or hot workings, in general, smaller microstructure. It means the grains are smaller in the size. There are still visible such twin lines inside the macrostructure. And if the last operation was the cold working, we can see again in the microstructure the slip lines. And if you are evaluating the metallographic structures, we can recognize such features there. And now to show you this example. This is the Dynasty 2 model of blade, and this is made from arsenic alloy of copper with admixture of arsenic and tin. There is only about 0.2 of arsenic and 0.1% of tin and 0.2% of nickel and little of lead. It means that this is slightly alloyed alloy of copper or non-alloyed copper with admixture of such elements. And what we can see in the microstructure, we can see homogeneous structure formed by grains of alpha copper solid solution. There are many annealing twins visible somewhere, and we cannot see any slip lines. It means that this material is fully annealed. And what we can see inside are these blue particles and these are non-metallic sulfidic inclusions. These are compounds of sulfur, copper, and iron. And as you can see on such image from backscatter electrons or secondary electrons on the left, these inclusions are changed into form. It means that they formed lines. And this is indicator for us that how intensively or how much the material was worked by mechanical way. We can sometimes see in the microstructure some lead particles, like here on backscatter electron microscopy image, and the lead particles are in white color. And what we can say, if we would like to conclude the production way, how this model blade was made, we can say that some repeated cycles of forging and annealing were applied, and there was applied a very soft hammering at the final step, but only on the edges of the artifact. And these all features are visible from the studied microstructure. If you look on another example, this is a model blade, again from the dynasty to Abydos. The microstructure is again formed by alpha copper grains. There is only 0.14% of arsenic and some admixtures of lead. What we can see, especially on secondary electron image here, macroscopic deformation lines, and these are indicators again of the shape and the direction of mechanical forming. And there are another features like these sulfidic inclusions, which are again formed in the line shapes. And we know from the microstructure study that the model blade of this type was made by forging and annealing. We don't know how oftenly these steps were repeated, but there was again applied the final cold working in the final step, but not only on the edges or surface of the blade, but in the whole mass of the material. This is very interesting example of microstructure study. We can see a full-size blade from Old Kingdom Giza, and this is made from alloy of copper and arsenic. This is the true arsenical copper or arsenical bronze with 5.2% of arsenic and little admixture of lead. There are fully recrystallized alpha copper grains with a little slip lines or slip bands on the outer surface of the sample, near the surface of the artifacts. But what is interesting, because there is a lot of arsenic, exceptionally a lot, there's more than 5%, we must to find somewhere the intermetallic phases of copper and arsenic, because the level of solubility arsenic in copper and solid solution of copper is about 3%, but all depends on the conditions of temperature and pressure and some specific conditions of artifacts production. But we can see some intermetallic phases of copper and arsenic on the grain boundaries of alpha copper, somewhere here. It's also visible on the image from the secondary electrons here. And also, together with such intermetallic phases, there are present some sulfidic inclusions and massive sulfidic inclusions. But as you can see, these are not deformed in lines. They are like globules, irregular globules, and they can be found somewhere. These non-metallic inclusions are composed by the mineral digenite. This is the sulfide of copper with high portion of iron and also the portion of selenium and tellurium. We are not able to say at the moment from where comes these sulfidic inclusions. There is one option that the sulfidic inclusions present in such copper alloys are the remnants of smelting of used sulfidic copper ores for production of copper. This is one option, or there's also possibility that such sulfuric inclusions should be associated with the alloying technology. It means with the addition of some sulfuric mineral or sulfuric material which contains a high portion of arsenic, also some portion of copper and iron, also selenium and tellurium, and this alloying agent should create such sulfuric inclusions. But to understand more in detail the origin of such inclusions, we need to study more than one exceptional samples of copper, arsenical copper artifact with a high portion of arsenic. And we can say about the production chain of such full-size blade that this was made by soft forging and annealing with final cold working. But we know that there was not applied so extensive cold working or hot working like in the previous case. There is another example. This is high tin bronze with almost 10% of tin, almost 0.5% of arsenic, and some admixture of lead. We can see slightly warped alpha copper grains with annealing twins again, and there is a large amount of slip bands inside of the grains of alpha copper, which are indicating the extensive mechanical working in the final step of production. And what we also can see in the microstructure are such lines, and these are again the sulfuric inclusions of copper, but in this case with high portion of iron, and these inclusions are very specific in a very great, very large elongation which formed them in the lines. And we can conclude that this blade was made by also repeated cycles of forging and annealing with final extensive forging. And this is a nice example of large amount of sulfuric inclusions inside of arsenical copper alloy. This is arsenical copper with almost 4% of arsenic, above 0.2% of tin, and little of lead. You can see again the recrystallite microstructure of alpha copper grains in the center of the blade, and some slip lines and deformation lines in the outer surface of the blade. It means that the blade was made again by the repeated cycles of hammering and annealing with the final hammering of the edges. And this image from backscattered electrons is clearly showing again the macroscopic deformation lines, which correlate well with the orientation of the sulfuric inclusions, as you can see. And this is a nice example of casted microstructure. This is not so common to see in our corpus of analyzed tools, because most of them were made by cold or hot hammering, but this is the dagger handle from New Kingdom, and this is casted piece with dendritic microstructure, as you can see. This is the alloy of tin bronze with almost 10% of tin and a mixture of arsenic and lead. What we can see are the dendritic structure of alpha copper phases, but what we cannot see are some intermetallic non-equilibrium phases of copper and tin, which were originally present on the grain boundaries, but due to the extensive corrosion of this artifact, these intermetallic phases were completely corroded, and there are visible only the remains of dendritic structure. And the microhardness measurements method was used in our case to characterize the real mechanical properties of copper alloy tools. The hardness values of arsenical copper tools originating from funerary contexts and settlement contexts were the subject of our interest. The Vickers hardness tests is a standard method using an intender in the form of a diamond tetrahedral pyramid. The method is based on measuring the size of the intender imprint in the surface of the material under the precisely defined load. This method monitors the material's ability to resist the plastic deformation from a standard source. This is the theory. And if we can simply be said that we can simply say that if we make some pyramid hole inside the flat sample surface, we will measure the size of this hole. We can see some correlation between the plasticity of the material and the hardness. And if we have simply a big hole inside of the material, it means that the hardness of the alloy is very low. The Vickers hardness measurements were performed by the microhardness tester on mounted and polished metallic cross sections of archaeological samples with a load of 100 grams and dwell time of 10 seconds. And from the series of measurements were statistically processed the obtained data, and the data were evaluated in the context of present metallic microstructures and the composition of the alloys. And if you look on the results, we can see that the microhardness analyses are able to determine the real mechanical properties of metallographically analyzed artifacts, and such information are for us very, very important if we would like to reproduce the artifacts with the real mechanical properties, and if you want to understand how was changing the hardness between the model tools and tools used for the real life and for the real use. In general, the hardness of unalloyed copper in annealed state is about 50 hardness Vickers units, and the alloying effect of arsenic and tin influences the resulting hardness only very slowly. For example, alloy of arsenical copper with 3% of arsenic increase the resulting hardness by only 10 hardness Vickers units, and the same amount of added tin to the alloy will increase the final hardness in approximately 20 hardness Vickers units. The hardening effect is caused mainly by the process of cold mechanical working, leads in the formation of numerous dislocations in the crystalline structure of alpha copper and their accumulation in the grain boundaries or near other solid phases present in the microstructure. And the presence of intermetallic phases in arsenical copper should further improve the hardness, but this occurs only under the equilibrium conditions at concentration above approximately 5-8%. It means that the alloying effects caused by intermetallic phases of copper and arsenic is not so common, because we are only exceptionally to see the alloys with such high arsenic content, and the main effect on a hardening leads in mechanical working. All the analyzed tools from the settlement context came from the Koromer area at the site of Giza, as you can see here in the picture. The exact location is here. The other tools from funerary context comes from the Abydos, Giza, and Aniba sites. And you can see here like artifacts made from arsenical copper alloy with recrystallized or slightly wrought microstructures reached the maximum hardness values about 111 hardness Vickers units, while intentionally wrought arsenical copper artifacts range between 143 and 161 hardness Vickers units. The level of hardening does not increase relatively to the amount of arsenics, but show a monotonous tendency independent on the arsenic content. The level of reduction in thickness is surprisingly the highest in artifacts with less than 1.1 weight% of arsenic, reaching values in the range of 65 to 88% of the original thickness. And artifacts with 1.8 to 2.8% of arsenic were wrought less intensively than their reduction in thickness is equivalent to 40 to 45% only. And what is interesting is this razor blade with exceptional 5.2% of arsenic, and this was only slightly forged, and its reduction in thickness is expected to be only in approximately 10%. And when comparing the obtained results with the hardness of practically used artifacts from a settlement context, we can see similar values of reduction in thickness and resulting hardness. But what is different is that the artifacts from settlement contexts tend to have higher arsenic content, but not the hardness. And this is very interesting. And the highest hardness values are achieved through a combined effect of cold mechanical hardening and the alloying effect of arsenic. The presence of arsenic in many artifacts is therefore associated with an effort to improve the color of the copper-based artifact rather than their mechanical properties. And on this image, you can see how the color of arsenical copper alloys and tin bronzes generally changes with increasing alloying element content. Here is non-alloyed copper. Here is alloy of copper and arsenic with 5% arsenic. Here is our tin bronze with 6% of tin, 10% arsenical bronze, and tin bronze with 10% of tin. The trends concerning the hardness of tin bronze alloys are somewhat different. Annealed high tin bronzes with 10 and 11% of tin reached a hardness about 84 and 97 hardness Vickers units. And slightly forged artifacts with 8 to 12 of tin reached a maximum hardness of 190 hardness Vickers units and were reduced in thickness only by 10 to 12%. It is necessary to note that the alloying effect of tin on resulting hardness of copper alloys is much higher than in case of arsenic. In case of tin, it's much higher than in case of arsenic. From the elemental analysis published so far, we can get a basic idea on the development of copper alloys used in early Egypt and partly also in Nubia. We can clearly say that arsenical copper had been widely used from the Nakada culture until the Second Intermediate period. And since the Middle Kingdom, arsenical copper alloys were gradually replaced by tin bronzes, while leaded tin bronzes were in use in the Third Intermediate period, at least. There are still some gaps in the knowledge of composition of Egyptian copper alloys artifacts, especially in the Middle Kingdom and the First and Second Intermediate periods. In general, very little is known also about the composition of artifacts from non-funerary contexts and from Nubian sites. However, some gaps in understanding the development of Egyptian and Nubian metallurgy have been partly filled by the results of current research. This graph does not take into account our new data from XRF analysis of large collection of artifacts in various European museums and our recent research in Egypt. Now, together with Martin, we are working on the publication of these large data sets, which will significantly refine the chronological development of copper alloys from the earliest times to the end of the New Kingdom. For the purpose of analysis of museum collections and for the field analysis, we use the mobile X-ray fluorescence spectrometer of type Bruker S1 Titan. The initial analysis performed by the non-destructive mobile X-ray fluorescence analysis is necessary for general alloy categorization and for selection of appropriate candidates for further sampling and application of more extensive and more expensive analytical tools like lead isotopes analysis or trace elements analysis. This XRF analyzer is equipped with 3 mm collimator. That means that the analysis is performed from an approximately circular array with a diameter of 3 mm. And this is performed directly from the surface of artifacts or from drilled metal samples. The X-ray beam is produced by a rhodium X-ray tube with a maximum power of 50 kilowatts. And this XRF is equipped with integrated calibration modes, including general metals, precious metals, geochemical analysis, and others. These calibration modes are used for automatic quantification of measured spectra, what is very useful and very fast. But the device also allows to us use our own calibration standards and real-time monitoring and control the measurements from the computer. During the analysis, the handheld measurements are occasionally used, especially in cases of very large objects, which is difficult to cover inside of shielding cover, but the most of analyses are performed inside the shielding cover, and there is almost no risk with the produced X-ray radiation to expose the operator of the XRF. If you look on this table, you can see the detection limits, which are established in ideal conditions. I will explain it later, what it means. And in most of relevant elements, there is a detection limit about 500 ppm, but this is not so bad. And in some cases, we are able to get even a little bit better results. And you can compare these detection limits, for example, with neutron activation analysis, which is very precise analytical tool to determine the trace elements composition of metallic samples. And these detection limits in case of neutron activation analysis are much better than in case of portable X-ray fluorescence. And during the performing of XRF analysis, it is necessary to ensure the optimal conditions for obtaining representative results. It is important to be sure that the surface of analyzed objects is as flat as possible, and the surface of such objects must be clean of corrosion products. In real practice, we know that this is mostly not possible, and we must to analyze the artifacts covered with the corrosion layers, but the obtained results in this case are not so precise, and we cannot use such data as in case of clean flat surfaces, and such results from corroded and non-regular surfaces are mostly semi-quantitative or only qualitative. It means that the data from corroded archaeological artifacts should be interpreted very carefully, and we are able to get some general information about the composition of the material, but mostly we can only say which type of elements are present there. The surface of artifacts must be clean from the soils and some other dirties. This is necessary. And in general, we are performing more than one analysis from one artifact. We are analyzing different parts of these objects to be sure that the unhomogeneity of the material will be covered by our analysis, and the data are in the next step evaluated by statistical method to get some average values. You can see on this plot the results of XRF analysis of two calibration standards. There are lines which corresponds to the given composition of the standards, and there are the data measured by our XRF, and you can see that there is a great correlation in many of analyzed elements, and some differences are also visualized here better because I use the logarithmic scale for data plotting. There's a little deviation in silver, gold, and cobalt content, but it depends on the parameters of measurement, and the deviation it's not so high. I will show you a few examples of XRF study of museum collections. For example, here this is the arsenic copper tweezers from C group Aniba. This object was completely cleaned from the corrosion products during the conservation treatment. And if you look on the plot, you can see the data which were measured by XRF and the data measured by neutron activation analysis from the sampled material from this object. What's the difference is the content of arsenic. In case of neutron activation analysis data, we can see higher content of arsenic, and it is most probably associated with the technique of used chemical cleaning, and that the arsenic from the surface layers was dissolved by this cleaning agent, and therefore our surface analysis should be performed on metallic surface, flat metallic surface. We can expect to get very nice results, but these are not so exactly corresponding to the composition of metal in the core of the artifacts because of the chemical cleaning. We can see a little bit higher lead content inside of metal, not on the surface, and there is a great correlation in the measured concentrations of other elements. This is the spearhead, it's unprovenanced, and this is the typical example of fully corroded object. But we were able to take sample from the core and to analyze it, and we can see some differences in chemical composition. By XRF method, we can see very high content of arsenic on the surface, also a higher iron content, lead content, a little bit nickel content. You can see that the composition which was measured on the surface by XRF, it's not corresponding to the real composition of the artifact because of the present corrosion layers. This is similar also for this first intermediate period or Middle Kingdom razor. This is also corroded, but on the surface of the object is only a thin layer of copper corrosion products, and we can see very similar measured content of arsenic made by XRF and ENAA, but what's different, there is also higher iron content measured on the surface of the object. This is very nice example, this mirror, because it was completely clean from corrosion layers during the previous conservation treatment. We can see different composition from the mirror disc and from the mirror handle. The mirror handle was made from alloy of copper arsenic and tin, but the arsenic and tin content is very low in this case on the level of admixture, but the mirror disc is made from the real arsenical bronze with almost 5% of arsenic. We have very great correlation in arsenic content in both sampling and analyzing spots, but what's different is the measured content of lead from the sampled mirror handle. There was measured more than 1% of lead, and on the surface was analyzed only a little of lead. With the lead, we have usually a big problem because, as I shown before, the lead is creating some insoluble globules inside the microstructure, and these are constant non-regularly distributed inside of material. And if you're analyzing the surface of the objects, we are not sure that there isn't any globule of lead or not, and we need to be very careful during the evaluation of lead content. If there is present lead in higher amounts, we need to analyze the surface of such objects from many spots to avoid some confusion with the irregular distribution of lead particles. This is the results of XRF analysis of the Dynasty 2 chisel from Abydos. The ratios of main elements are almost the same, but there is a very deviated content of iron measured on the surface of the objects. This is also associated with the corrosion deterioration of the object, and some admixture elements which were analyzed by ENAA are mostly below the detection limit of XRF. This is ads from New Kingdom Aniba, also slightly corroded on the surface, but the compositional results obtained from XRF and ENA analysis are almost corresponding, with exception of arsenic and iron. This is also an example of almost completely corroded piece where the interpretation of obtained data is very difficult. We are usually creating some 3 general categories of copper alloy objects. The category 1 is composed by the uncorroded objects with the metallic surfaces. There is category 2, where are included objects with small thin layer of corrosion products on the surface, and we have the group number 3 with a large amount of analyzed pieces, which is composed by copper alloys in high degree of corrosion. And in the group number 3, we are not usually taking this obtained data into the final statistical evaluation because these are not representative, and this is also case of these ads. And to conclude, our current research on early Egyptian copper metallurgy is carried out at the 2 main levels. Together with Martin, we focus on the analysis of large collections of copper alloy artifacts, which are stored in European and world museums. This research includes XRF analysis of a large set of artifacts and the identification of suitable candidates for further more detailed analytical study, for example, using ENAA, ICP-MS, or multi-collector ICP-MS. These methods are very useful for example, provenance analysis using the lead isotopes analysis, or for analysis trace elements composition. This is one part of our research. And there is another level which we are working on in parallel to this, and we focus the analysis of artifacts which are related mostly to the metallurgical production steps And it means that these type of artifacts are mostly slags, crucibles, spirals, some metallic byproducts, and other type of material. And this kind of material is generally preserved in a very large quantity within the metallurgical workshops in the vicinity of some settlement contexts, for example, in Giza, Elephantine Island, or Tel Retaba and other sites. And we need to work on this kind of material directly in Egypt. And it means that we are limited in the types of use of analytical tools. We can work with the XRF, we can work with metallography, microstructure analysis, and we are able to use the scanning electron microscope with EDS analyzer. But the information what we are able to obtain from such a kind of material is very necessary to understand the technological aspects and the background of copper metallurgy production in early Egypt, and such type of information are extremely valuable for us. Thank you for your attention.